I am going to be focusing a little bit on a more site-specific application of the NGA West 2 model. So now that these new models have been developed and they're out there, one of the questions I get asked almost on a daily basis for projects is, how's it going to impact my site or my project? And unfortunately, usually I have to say, well, it depends as to what's controlling, what sort of features of these models are different from the 08 versions to the new versions. And so I'm going to go through a very case-specific example here for Diablo Canyon and sort of look at some of these features and some of these changes between the model features from 2008 to the current 2013, 2014 NGA West 2 models. Just going over a quick overview of my presentation, I'm going to start off with the general seismic setting and controlling sources. Most people might be more familiar here in California with Diablo Canyon, say the other three sites that we are giving these touring presentations at, being Seattle and Salt Lake. But I just want to go back in case some of you aren't familiar with Diablo Canyon in the sense of what's controlling the hazard at the plant and sort of what are the controlling seismic sources. Then given that background information, I'm going to go through a couple of deterministic cases where I start looking at certain features of the models and how they've changed from 08 to the current new models, and that's specifically the site condition factors or features of the models. And an important part is this whole hanging wall issue. Mark Peterson talked this morning about in the national hazard maps, this might be something you need to consider in more detail as to how ground motions on hanging wall sites are modeled and captured in the epistemic uncertainty. Then I'm also going to talk about the large magnitude of close distances. So we'll see in the next couple of slides that for Diablo Canyon, based on the seismic sources, we're concerned about a large magnitude at a very close distance. And then finally, I'll talk about sigma, and at the end, I'll put it all together for one quick slide showing some hazard results for Diablo Canyon and how there's a change in the ultimate hazard curves given the new models versus the old models. Just to orient people, if you're not familiar, Diablo Canyon is located here on this red star. This is a map showing the central coast of California. It's about halfway between here and Los Angeles, down along the coast. It's a beautiful piece of central California coastline. The power plant is located with the red star, as I mentioned, and what you'll see here is the background seismicity or the recorded seismicity for a time period about 1987 up to 2008. So a fairly substantial amount of time window, and you can see there's a lot of seismic activity. A couple of sequences to point out is this first one here is the San Simeon earthquake, a magnitude 6.5 event that went off about 10 years ago. And then in the upper right-hand part of this figure, you'll see the San Andreas Fault here mapped out with the tightly clustered seismicity. And this little clustering that starts to just go off the edge of the plot, that's the much anticipated Parkfield event, the magnitude 6 event that finally occurred in Parkfield. And so you can see that for Diablo Canyon, you're not relatively close, but you do have a lot of seismicity in the area. The distance from the plant to the San Andreas Fault is about 80 kilometers, just for reference. And then you can see you have some associated seismicity off the coast and also some map fault traces throughout the area. If we move in now and look at a close view of the plant and sort of the topography, this is again the central coastline of California. The plant is the red star here indicated. And there are basically four main sources, and I'll show a little bit later in a couple of slides that these are basically the four sources that control the hazard at the plant. And so I'll walk through them briefly. The red dots here off the coast here, that's the Hosgui Fault. It's nearly vertically dipping 80 to 90 degree strike slip fault. It's capable of moderate to large magnitude events up to magnitude 7.5 and or larger, depending if you want to include the USURF option in the source characterization. So that's one of the main sources. The other source that's shown here in the green, that's the Los Osos Fault. Los Osos Fault is a reverse thrust fault, and it's the main reason why these Irish hills, this geologic feature, this block, is actually here and has elevation topography with it. So it's dipping to the southwest. So that means the plant is located on the hanging wall of the Los Osos Fault. So as we think back in ground motion models, either from the 2008 or the current models, the hanging wall motions tend to be larger than footwall sites. So that's one thing we need to consider. The next fault that is important to the plant for the hazard is this blue trace, and that's the San Luis Bay Fault. Now the San Luis Bay Fault is again a reverse fault that dips in the opposite direction. It dips to the north. So again, unfortunately, the plant is located on the hanging wall site of this dipping fault. And all these faults project all the way to the surface, so they're surface traces. And then finally, the last one shown on here is the yellow dots. That's a recently discovered shoreline fault, and this was discovered and studied in great detail in the 2011 shoreline report, which you can find if you do a Google search under shoreline report 2011. And in that report, it was sort of the characterization of that source and as well sort of the implication of the hazard at the Diablo Canyon plant site. It's a vertically dipping strike slip fault. The closest approach is about 0.6 kilometers. So again, this is something we need to consider when we're looking at using these GMPEs. If we look quickly at the deaggregation, just to make a better understanding of what controls the hazard of the sites, I've got two figures of deaggregation plots, and the one on the left is for PGA, the one on the right is for 1 second or 1 hertz. One thing that's different about nuclear power plants as compared to, say, building code applications is building codes are usually 2 times 10 to the 2% 50-year or 2,500-year probability level. For nuclear power plants, we're looking at the 10,000-year return period, 10 to the minus 4 and also 10 to the minus 5. So we're a lot further out on the hazard curves. So anything that would impact things out there, for example, as a sigma, would be a critical thing that we want to investigate in further detail and make sure we fully understand it. If we look at these deaggregation plots, which are all for 10,000 year, you can see in both cases that it's being controlled by the close-in moderate to large magnitude events. This axis here is the distance range, and the first 3 bins here go up to a distance of 10 kilometers. So again, we're looking at very close distances on the order of 10 kilometers and less. And then these are the magnitude range, and you can see the main peak comes in at about 6.5 to 7 in magnitude. If we look at sort of the tectonic setting, people might think, okay, well, the San Andreas Fault is out there, it's capable of producing large earthquakes, it has a pretty high slip rate, so I would expect that might contribute at the longer periods. It turns out that it doesn't really contribute because of the close proximity of these 4 faults. Looking at the 1 second again for 10,000 year, you can see this little blip here is a contribution from the San Andreas Fault. So it's not perfectly flat, there is a little contribution, but you can see relative to the peaks as to what's controlling the hazard, it's really being driven by these 4 faults that are really close to the plant. Given that, what we're doing right now is a SHAC Level 3 study for both not only the source characterization team, but the ground motion teams. And so this sort of drives us to really focus on some of the features of these new models, and not just the NGA West 2 models, but also other models that are out there, GMPEs that are available, as to how these features are modeled and how they're captured in the individual models. One of the first features that's of importance to Diablo Canyon is the shear wave velocity. So all of the NGA West 2 models now are defined as a function of VS30. At Diablo Canyon, it's a little bit different than we typically find in California in the sense that there are 2 borehole stations at the plant with downhole profiles. And it turns out if you do the average VS30 for those 2 profiles, you get a value of around 1,100 meters per second. So it's a very hard rock site for, quote, California rock. It's a lot harder than you would expect if you just went to a typical California rock site along the coast. Now, given that, we have to sort of make an evaluation as to how well these models are doing and how well they're predicting ground motion for such a high VS30. So one of the questions we had was, do we want to use a VS30 of 1,100 meters per second, or do we want to pick a softer VS30 and use that as sort of our reference and accommodate any sort of site response as a sort of post-hazard process in a typical site response analysis? In going back and looking at what went into these models, that's one way we can evaluate how confident we feel about the prediction at these high velocities. So on the left-hand side, I have a plot showing the database of VS30 values from the 2006 or the NGA West 1 database. And on the right, you have the same plot, but it's for the updated NGA West 2. You can see, as Tim has talked about, there's a substantial increase in the number of recordings or number of VS30 values, both for the measured and estimated. But if you focus here on those velocities that are, say, greater than 1,000 meters per second, you can see we almost had none back in the 08 version of the database. And we've got some now, but not a huge increase. So that's one of the considerations in applying these models is, do we want to use these models, or do we want to investigate what happens to these models in their extrapolation or their prediction of ground motion for data that they're very limited in trying to capture. This is just a quick summary slide showing the different ways that the 5 individual teams are used or have parameterized the site response. So on the first column, you have the 5 individual teams with their acronyms, and there are a couple of additional letters now that have been added for the new models. The middle is sort of the parameterization that they have for the 2008, the NGA West 1 models, and on the far right is the similar thing, but now for the NGA West 2 models. For the most part, they're very similar in the sense that they're all now a function of VS30. I should point out that the Idris model in the 2008 vintage was defined based on 2 bins of VS30 values. So he had 450 to 900 meters per second as one bin and greater than 900 meters per second as the second bin. So in other words, if you had a VS30 of say 760 or 500 or 900, you'd have the same predicted ground motion values from his old model. He now has a linear term on VS30 values, so you would no longer get the same predicted ground motions for those different VS30 values. He also has a limit on his model of 450 meters per second and greater. So again, if you're thinking to use the NGA West 2 models in your project or in your application, that's one of the things to consider, is that his model would not be applicable for a softer site. The other thing that the NGA West 2 modelers have come up with is for their depth to the given boundary, whether it be the 1 kilometer per second velocity boundary or say the 2.5, is that because we now have this big database of enhanced records and metadata associated with them, they're able to come up with estimates of those parameters that are more regional. And so there might be an estimate for, say, just California data. There'd be an estimate for, say, Japanese data, an estimate for data from China, and a data from Turkey and Italy. So this way you could sort of tweak the models and apply it to your specific project if you weren't, say, in California or you wanted to make a modification for a different region. I'm going to go through a series of median plots and spectral plots, and I'm going to walk through a couple of different cases and sort of highlighting the differences between the old and the new models. So the framework of what I'm showing are going to be very similar. The parameters and the actual spectra are going to change. So on the left-hand side, what I'm showing, and will always be in color, are the new models. So the 5 NGA West 2 models. And on the right are the same models, except for they're the vintage 2008 NGA West 1, shown in black and white. The line types are exactly the same. The only thing that changes is the color and obviously the values. For this first set of series, what I'm going to be showing is for a vertical strike slip fault at a distance of 30 kilometers. Now there are a couple of new parameters that are needed for some of the GMPEs with the new models, and I've listed some of those parameters at the top of this title block. One of them is the top of rupture, or depth to the top of the rupture, TOR. And a lot of times people have asked me, I don't know what that'll be. I don't know what that is. There are recommended values in the NGA West 2 documentation, especially for specific models, as to correlations between, say, magnitude and depth to the top of rupture. So if you're trying to apply these models and you're not quite sure what value to use, the best recommendation is to use the default correlation values provided in each of the individual team documentation. One of the models chose not to use top of rupture, but chose to use hypocentral depth for their depth scaling parameter. And so you can see here for this case, I've used a depth of just over 10 kilometers. And again, that's using the default empirical correlation recommended value from their model based on the magnitude. What I'm showing for this first case is this is now all for a VS30 of 550. And so it's a little bit softer, but I'm going to walk through a couple of VS30 values and point out some of the features. The first thing to note is that if you look out here at the longer period, say focusing at 1 second, you can see that the new models are in closer agreement than they were back in 2008. And then as well, as you look at the intermediate to high frequencies, or the shorter periods, it's a little bit better distribution. There's a little bit tighter clustering in the new models as opposed to the old models. Now the reason I chose a 7 at 30 kilometers is because this is sort of in the meat of the database. It's not sort of at the ranges or the edges of the database where sort of extrapolations and considerations were made in the models and how they would extrapolate to those ranges. If we now move to a little bit stiffer site of 760, so again, it's the same scenario earthquake in the terms of the geometry and the distances and the magnitude, but all I've changed now is the VS30 value. So this is again for a reference typically of 760. You can see a couple of things is that, again, at the longer periods, we're getting a better agreement than we saw back in 2008. And I think that's probably just an artifact that we have a lot more data and a lot better refinement on the metadata that went into the new database compared to the 2008 database. And then as well, there's some other interesting features that are coming through. One is that if you remember here, the Campbell-Brezonian model, As you're going to a higher shear wave velocity, they're starting to get a shift in the spectral peak. And I'll talk about that in more detail when I look at the averages. But that's sort of to be expected in the sense that if you do a simple geotechnical analysis and you go from a softer site to a stiffer site, you would expect that peak to be shifting to a higher frequency. So that's something that sort of models or captures what we would expect to see in other disciplines. If we want to look at things in the longer period and we look at spectral displacement, you can see here again on the left we've got things plotted in a linear scale, so we can sort of see those things, because before I was doing things log linear. There is a big range now, and this is one of the takeaway points from my presentation, that if you look at individual models and how they changed from 2008 to the current NGA West 2 models, you can see large differences for certain scenarios or certain cases. However, I'll show in a couple of slides later, if you look at the average among the 5 from 2008 to the new versions, there isn't that significant of a difference. And so this is sort of emphasizing that effect in the sense that this high curve up here now is the Idris model for the NGA West 2, whereas before his model was down here at this level. And again, if you remember, this would be a similar plot for the old model, for his model, for different VS30 values within this bin, because he doesn't have it as a function. This is now a function of the VS30 value. If we finally go to what would be more typical of a site-specific VS30 value for Diablo Canyon, you can see these are the two comparison plots. We're starting to see even a bigger spread in the predicted motions, especially at the intermediate and high frequency range. But again, at the longer periods, you're starting to still maintain that tight clustering or agreement between the models. And again, as I mentioned before, the Camel-Bezonia model is showing this shift in the peak as we get to a higher shear wave velocity. If we now just summarize those and we take the average of the 5, so what I'm showing here is the red curve is the average of the new NGA West 2 models, just equally weighted. The blue dashed line is the average of the old 2008 vintage models. You can see some interesting features. One, as you go up in shear wave velocity from 550 to 1100 meters per second, you get a reduction in the ground motion amplitude, and that's sort of to be expected. And then the other thing that I mentioned before is that we're starting to see a shift in the peak of the spectrum in sense of the spectral period from the new model, whereas the old models all peaked at 0.2 seconds. And so you can see this was 0.2, 0.2, 0.2. Now we're starting to see this shift to a higher frequency. It's not as severe as or drastic if you compare just a Camel-Bezonia model. So again, this is emphasizing the fact that if you compare individual relationships, you can see some significant differences, but when you compare the averages, it's not as significant as to be expected. The next important feature that's obviously very critical for Diablo Canyon and would not necessarily be applicable to all sites, but is this whole hanging wall issue. And so it's how do we model the hanging wall sites and ground motions associated with that. So this is just a similar summary plot showing the way the parameterization was handled in the old 2008 models and the new NGA West 2 models. There is one typo in your handout booklet, unfortunately, that got through. Down here on the bottom, the Idris model for the NGA 2013 model should be a hyphen. He doesn't have a hanging wall model. And so if you want to make note of that, that'd be great. And just going through, as I just mentioned, the Idris model does not have a feature showing the hanging wall. So he would predict the same ground motions for hanging wall and footwall sites at the same distances, whereas the other models have an accounting for that. And one of the models, the BSA team, has an indirect accounting for that in the sense that their distance metric is JB distance. So if you think about it, as you're going over the hanging wall, your JB distance would go to 0 as you're over the surface projection, and it would stay at 0 until you go over to the footwall side. And so those ground motions would all be constant. And so that's the way they've captured and they feel they can model the hanging wall effect. The other modeling teams actually have additional factors that get applied to their median ground motion model as an additive term. I'll go through a simple example of showing this effect, looking at a site on the hanging wall and a site on the footwall for a very simple magnitude 6.8 earthquake. It's shown in cross-section here. The rupture distance between these two sites is always the same, so it's 7.6 kilometers. That means over the hanging wall site, it's a little bit different RX distance, and so Tim was talking about the RX distances earlier, so it's a little bit different. You can see down here it's 7.6 on the footwall because it's just a horizontal distance. On the hanging wall site, it's a little bit larger. Again, over the hanging wall site, your JB distance would be 0, and over the footwall site, your JB distance would be 7.6, just that horizontal distance. For simplicity, I've taken a 45-degree dipping fault that comes all the way to the surface with a width of about 15 kilometers. And again, I've used a hypocentral depth as predicted by the recommendation model and the Camel-Bezonia model. If we go to the spectra now, again, these are for median spectra. These are all for a shear wave of 760, so I've switched back to a reference site condition of 760. These are the comparisons showing the new models and the old models, and there are some interesting things to point out here. One is that in the old models, we were seeing a big spread in the range in the models in predicting ground motions over the median, over the hanging wall sites, and we see that as well. The peak levels are about the same, and I'll show you in the next slide on the averages that they turn out to average to be about the same, but you see the same type of spread in motions. The other thing to note on this slide, of course, is this lowest model here is the Idris model, and again, as I noted before, that model doesn't have any factors for the hanging wall, and so all the other 4 models have been increased relative to, say, their footwall sites, and you'll see in the next model that Idris model is very comparable to the other models for footwall sites, but because he doesn't have a hanging wall factor in his model, it actually ends up being lower relative to the other models. This is now the same plot before the footwall sites. So as I was just talking about, the Idris model now falls right in the middle of the footwall sites. And so if you're on the footwall site, all these models are predicting very similar motions, whereas if you're on the hanging wall site, there's quite a range in the prediction of the ground motion models. It's about the same distribution that we saw before for this case. So again, this is something that needs to be applied on a project-by-project basis once you know sort of what's controlling your seismic hazard at your source or what's important. And then finally, if we just look at the averages I had mentioned, there isn't a significant change. There's a little bit of shifting here and there, a little bit of increase, a little bit of decrease, but overall, the changes are not huge, as you would see when you compare individual models one by one. The next thing that's important to Diablo Canyon is, of course, these large magnitudes at close distances. So again, I mentioned the shoreline fault comes within a kilometer or so of the plant. The Hot Scree fault is about 5 kilometers offshore from the plant, and so you've got the potential for large earthquakes on the order of 5 kilometers or less from the plant. And so what I'm going to be showing here is a couple of spectra, again, median spectra for a VS of 760, but looking at magnitude 7.5 at 5 kilometers and at 1 kilometer. For these, I've allowed the fault to rupture all the way to the surface and a hypocentral depth of 10 kilometers, 10.2 kilometers. So the first plot is showing the results for a distance of 5 kilometers, so basically similar to what you would expect from the Hot Scree fault. And again, you're starting to see a bigger spread out here at the longer periods than we saw before for my case of magnitude 7 at 30. There are a couple of reasons for that. Is again, now we're starting to get off to the edges of the database distribution, and so this is where the models tend to sort of treat things differently and they behave differently. And so you're starting to see a bigger divergence of the models than you saw before for the cases in which you're in the midst of the database, the real heart of the database. In the intermediate to higher frequency range, you're starting to see similar, if not a little bit larger spread compared to the 2008 models. But overall, there's a pretty good similarities between the visual averages if you look at it that way. Now if we move into 1 kilometer, so this is again, distances that are very close from large magnitude earthquakes where the data sets really starts to drop down and we start to lose the number of data points that go into the data set. Again, you can see over on the right-hand side in the black and white, these are the 2008 vintage, and then these are the new 2013 NGA West 2 models. You're still seeing a spread out here at the longer periods. There is another feature of the Idris model that's starting to come through that is observed when you have large magnitudes at close distances. His PGA is here at about 0.8, this blue curve, and then his peak is up at 1.4. Now, if you think in the traditional sense, if you go from PGA up to 0.2 seconds, if you take that to be your peak, whether it be in building code space or wherever it might be, that ratio is usually around 2.5 or 2, or sometimes it's even fixed in the building code to be 2.5. The Idris model is now predicting a ratio of quite a lot lower, less than that, of around 1.7, 1.8. So this is a feature of his model that if you were in a situation where this was a critical type of source that was controlling, you might want to consider or reevaluate in more detail as to how you want to include that model or weight that model or use that model at all. So these are some of the features and some of the things I think when you take these new NGA2 models and use them, you need to sort of really understand and comprehend before you just blindly throw them into your equations and use them. And then this is just a summary again, where you see very similar results when you take the averages for both 1 kilometer and 5 kilometers. So the last thing I'd like to talk about before I show some hazard plots is the sigma models. And on the top, I'm showing the total aleatory sigma for magnitude 5.5 strike slip event at 30 kilometers, and then below that is the same thing, but for a magnitude 7 at 30 kilometers. So again, this is in the middle of the database range. It's where we have a lot of data. We should have some good confidence in that. You can see that in general, the colored lines, which are the NGA West 2 models at the short periods, the high frequency, are a little bit higher. And as well, for the smaller magnitudes, they're higher. And so those are sort of some trends that you're starting to see. At the longer periods, you can see that the old models tend to predict a little bit higher sigmas than the newer models, so that's also a change as well. And so when we do the hazard analysis for Diablo, as we're doing, all of this gets put into the hazard analysis in the sense that you take the median motions and as well as sigma. And as I mentioned before, for nuclear power plants, we're looking at 10 to the minus 4 and 10 to the minus 5 probability levels, so we're quite a ways out there on the hazard curve. And so things like sigma are a very important thing in our analysis. So just before my last summary slide, I'm going to show one figure showing hazard curves. And I should mention that this work is ongoing right now. We're doing a SHAC level 3, as I'd mentioned before, study for Diablo Canyon. In terms of the ground motion, there's actually a teaming up of Diablo Canyon, and there's a nuclear power plant in Arizona. And the ground motion teams are actually combined now, and they're coming up with one ground motion model at the end of the day. They'll come up with one model that's applicable for not just Diablo Canyon, where these things are important, but also for Arizona, which raises some other interesting critical things to look at and investigate. When we put everything in together for Diablo Canyon and we run the hazard, I'm showing two sets of hazard curves, one for PGA and one for 1 second. PGA is on the left and the 1 second's on the right. As you'll see there, it says normalize PGA and normalize 1 second. And what that means is I've taken the x-axis values, the ground motion values that you typically plot, and I've normalized them by a factor. And that's just because what we want to look at here is sort of the relative changes. We're not as concerned at this point in the analysis at looking at what are the absolute values, what's the 10 to the minus 4 value. We're just looking at to see how does the hazard curve change. And so we've normalized these by a given amount and just looking at sort of the comparisons between the old and the new. So similarly to what I'd shown before for the averages, the red curve is the normalized PGA hazard curve using the 5 NGA West 2 models, and the blue dash is for the NGA West 1 models. And I've applied equal weights to these. I've run the hazard, and this is for PGA. You can see it at 10 to the minus 4, where we're interested for nuclear power plants. There's been a slight decrease based on the new models. And so that would be a combination of the median prediction changes between the individual models and as well as sigma. And then if you look at the 1 second, you can see there's a slight increase in the relative hazard of the site. But overall, there's a pretty good comparison over a wide range of probability levels between the old and the new models. And so that sort of just reiterates that when you're looking at a combination or an averaging over the 5 new models with the old models and how it impacts the hazard, for Diablo Canyon at least, it's not a significant change, but if you were to break it down and look at these hazard curves, these types of hazard curves for individual models, you'd probably see a significant change. So just in summary, what I hope I've shown to people and people can take away from this is that there's a significant change in the individual models when you're making these comparisons, but when you average them out over the 5 models and compare the averages, the results aren't as different, and they're actually quite similar. And then as well, I've talked about some specific examples in looking at the VS for the rock conditions, the hanging wall site factors and models, which is important, and the large magnitude at short distances. And I think that in going forward, as I started with my opening presentation here, as people ask me all the time, how's that going to impact my project using the new models? I think these are the types of things that one needs to consider, especially if it comes down to the point of developing weights, whether you want to equally weight them or whether you want to come up with non-equal weights for the project, just so you can understand how the differences have changed in the ground motion models before it goes all the way in, say, to hazard or all the way into the design spectrum. Thanks. Are there any questions?